Let me start recording and let me take this opportunity uh, to introduce our guest speaker today. So welcome all of you. Welcome Professor Atul Dixit to this session. So this is today's first guest speaker session, and we have a really amazing person with us. I just I was just like to start with a small story. It's not story exactly. So all of you would have been at some particular point of time got to know who Srinivasa Ramanujan was and what kind of math he did, and you have some idea. And then his story, when you read or you watch his movie, it always gives you goosebumps, right? And you feel that, oh, I wish I could do something like that, and so on and so forth. Or I wish when I grow up I can understand some kind of math that Ramanujan did, and how did he get all these things. So we are very lucky to have somebody like Professor Atul with us, who was as inspired or at least as inspired as you guys when he was of your age, and he was inspired by Ramanujan's work, and he continued to pursue mathematics. So he did his graduation in India. He did his master's in Texas University, Texas Tech University, and then he went to do his PhD from University of Illinois, Urbana-Champaign. And those of you who don't know, that's the place where there is a great mathematician who has pioneered in the, who has been instrumental in bringing out Ramanujan's work, which would have been lost otherwise. And his name is Bruce Berndt. Some of you would have heard his name. So Bruce Berndt is one of the authorities in Ramanujan's work. And Professor Atul Dixit, being very passionate about math and Ramanujan's area, went ahead and he pursued PhD in math under the guidance of Bruce Berndt. So he is one of those few Indians who have pursued Ramanujan's work under Bruce Berndt. And then he did his postdoc fellow from Tulane University in the US. And then he continues to teach. He is assistant professor now in the Department of Mathematics at IIT Gandhinagar. So he is well within our reach. We can go and trouble him sometime when we go to Gujarat. So he's yes, definitely. So he has a lot of honors and awards to his name. Not take name all of them, but recently this year he got Gabor Zigo Prize, which is given to mathematicians who are below 40, and he's the first Indian to receive this prestigious award. He's also the recipient of various awards in excellence in teaching, excellence in fellowship, excellence in research, and a lot of prize and fellowship to those achievements. And he has authored he has contributed more than 50 research articles in various journals, and most of them have been in the area of Ramanujan's work. So we have somebody who day in and day out thinks about Ramanujan, and he kindly agreed to come and do a session on Ramanujan's work on theory of partitions with us. So we are very happy, Professor Atul. We would like to welcome you to this particular talk, and we all look forward to hearing from you. So thank you so much.
Thank you, Vinay sir, for a very kind introduction. I'm very happy and privileged to be a part of this Raising a Mathematician Foundation.
Just one more thing to the students.
Yeah.
Thank you. Yeah. So no, just wanted to tell the students, if you have any questions, don't unmute yourself and ask directly. You can do a raise hand, and then we will take questions as we go ahead. Okay, questions or comments. Sorry, over to you. Sorry.
Sure, no problem. Yeah, thanks very much. I'm delighted here to be a part of this Raising a Mathematician Foundation group, and I would like to tell you something exciting about theory of partitions. This subject is something which requires minimal introduction, minimal. I mean, basically, if you know few concepts, you can from day one start on exploring things and then find about what kind of new results you can get, as opposed to some other areas which require lot more conceptual understanding first, and then, not to say that this is an easy area, but of course this is something which is very exciting. By the way, is my voice clear or is it coming with some sort of disturbance?
Yes, sir.
It is clear. Okay, thanks. So let me share my screen. Yeah. So I'm going to introduce for you the area of partition theory. And okay, yeah. So what is a partition? A partition of a positive integer is a finite non-increasing sequence of positive integers which sum to n. Now let's see this from taking an example. So I just take how many partitions of 5 there are, which means I try to see how many ways there are to partition 5 as sum of smaller numbers or up to itself. So 5 can be written as 5 itself, or 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 3 ones, and then 5 ones. Okay, but make sure that you see one particular thing which we are assuming, and that is 4 plus 1 is the same partition of 5 as 1 plus 4. So the order doesn't matter. That's why I have written here a canonical way of representing, that is non-increasing sequence. So you start with the largest part, then the next largest, and so on up to the smallest part. For example, here the largest part is 3 and smallest part is 2. Here the smallest part is 1, largest part is also 1. So you are going really this 2 plus 2 plus 1, 2 plus 1 plus 2, or 1 plus 2 plus 2 all constitute the same partition. So there are 7 partitions of 5. So in general, if we take a number n and we say that, okay, how many partitions of n there are, we call that by a number p of n. And so p of 5 is equal to 7. Okay, so as simple as that. All of you must have watched the movie The Man Who Knew Infinity. If not, I will really urge you to watch. This is a movie on Ramanujan. And there is a scene in this particular movie where Ramanujan is sailing to England on a ship, and he's dejected because he is having to leave his family. And there is a fellow Indian which kind of unnecessarily asks him about, okay, England is 6,000 miles. Can you imagine? And then Ramanujan says, I have known larger numbers. He very curtly replied, at least in the movie, it is shown like that. I don't know whether such a incident ever happened, but this is some of the things you in a movie they are cinematized. So he says, I have known larger numbers. The point I want to make here is probably Ramanujan is talking about the partition values, because you see, even though p of 5 was 7 and p of 4 is 5, something which is doable, p of 50 is, you can see here, 2,04,226. P of 100 is this 9-digit number. So beware, if you start calculating partitions of 100, very soon you will want to abandon that process, okay? Because there are too many partitions. So this partition function seems to grow exponentially. Very soon it becomes very large. So we'll see how exactly it is. So here is another scene in the movie. Again, such a thing did not happen in reality. But anyway, this is one of the most favorite scenes of mine whenever I have watched this movie. By the way, I would urge all of you, if you are feeling disappointed in life, if you are having no fun in life, I would urge all of you to watch this movie. It will really change our perspective, because you will see how somebody who was under so much difficulties in life, struggle, poverty, etc., could achieve so much, irrespective of all these difficulties that he had. I mean, that did not deter him from achieving his goal. So in this movie, here is the famous combinatorialist, Major McMahon. Here is G.H. Hardy, and here is Dev Patel as Ramanujan. And it so happens that Hardy and Ramanujan are about to make a very startling discovery. That means you can take any number you don't have to really calculate partitions of it by hand. If you can get some sort of formula by which you can calculate the exact number of partitions, then that should do the job. Okay. Otherwise, how do you calculate P of say 1 million? I mean, it will probably take us a year, and plus there may be mistakes. So we may not be able to get the actual number. So these two go to Major McMahon, who is a very fast calculator. So McMahon was faster than Ramanujan in calculating mathematical expressions, square root of some large numbers or other. Ramanujan was also, of course, very quick, but McMahon was believed to be a bit faster. So they go to him, and as such, what it happened in reality was that they had a formula and they wanted to check with McMahon whether their formula is correct. So they asked McMahon to check up to P of 200. And then McMahon provided a table, and then they checked that, okay, their formula matches. In the movie, what it is shown is that McMahon is shown to be not appreciative of Ramanujan and of Hardy, especially regarding this discovery. He is of the belief that, okay, partitions are to be counted by hand and not in this particular way that they are thinking. So then they say, okay, then we tell you to calculate P of 200, up to P of 200. And then McMahon does it in a month. And then after a month, they meet. And this is this scene. So McMahon asks, what has your formula given you? And here is what Ramanujan has. And here is what McMahon has. And you see that they match, except for one digit, which is actually the mistake from the director's side. This is an oversight from the movie producers or directors. Actually, these two are the same numbers. So this should be a 9. Okay. So they get exactly same formula, except that because Ramanujan and Hardy's formula comes from another method, it has a fractional part also associated with it. But we know that partition of any number of partitions of any integer itself is an integer. So we just discard of that fractional part. So this is after discarding that fractional part. Okay. And then here is McMahon in complete awe. And you can see Hardy looking at McMahon as if, I mean, see, we were telling you that we'll be doing this not by hand. Anyway, so what was that formula? This was this P of n asymptotic to this exponential growth that we were believing is really true. But it's not exactly exponential because you have to divide by this 4n root 3 as n tends to infinity. But what does it mean? It means that when your n tends to infinity, this upon this tends to 1, or limit n tends to infinity of P of n over this quantity is equal to 1. Which means that if you go very high, if you take a very large number n, these things will almost match. There may be some difference. That difference will be 0, tending to 0 as you let n tend to infinity. Okay. So now this is something that I'll come back to as to how you get asymptotic formula or even an exact formula for partitions. But now what I would like to really do is to look at some combinatorialistic approach towards partitions. And that was done by Euler. What does combinatorics mean? Combinatorics mean some sort of counting. Okay, you have some sort of counting procedure and you study various counting methods. So what is a generating function? If you are not introduced to generating function, here is a very nice quote from Herb Will. So he says that a generating function of a sequence is a clothesline on which you hang all elements of your sequence. Which means that if you have a cupboard, you have a rod on which you have a lot of hangers and with clothes put in there. And you want to take all of these clothes from one room to another room. One way to take it is just move the hanger. Take that, take that rod. And along with the rod, you have all of the hangers and all of the clothes. Okay, so he's saying a generating function does a similar thing. What do we mean by that? So suppose I am interested in partition function P of n. What if I actually take P of n times q to the n and then form an infinite series with that? What does it mean? I am taking P of this n goes from 0 to infinity. So I will be adding all such values at n equal to 0, n equal to 1, 2, 3, 4, so on up to infinity. So it is basically P of 0 q to the 0, which is P of 0. Then P of 1 times q, you have 2 times q square plus P of 3 times Q cube plus dot 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 up to infinity. So this is called as a generating function because whatever expression for this you are going to get, and we are going to soon prove that that expression is this, which was shown by Euler. This generates these partition values. So it is called as a generating function for P of n. So how do we get this is what is the question. But what I'm now moving to is that you have an analytic expression for this. This is a function of q, f of q, let's say, if you want to call it. It's a function of q. So you have an analytic expression for generating function for P of n. Now you are moving from just P of n's as values to something which is a function which you can say is encapsulating the information about the partitions of every integer n. Okay. Now, one thing that we want to make sure is that we understand that when we go from finite sums to infinite sums, there are questions of convergence that come into picture. And for example, this is an infinite series. And when does it converge? If it gives answer as infinity, it's not something that I'm really interested in. Right? How do I study something which is always infinite? It is infinity, that's it. But if it is a finite thing, then I would like to find out what properties it has. Now, you can regard this generating function as an infinite degree polynomial. Okay, with a polynomial of finite degree, there is no question of convergence. But with infinite degree, you do have convergence aspect. Similarly here with an infinite product. So as long as you have q to be a complex number such that mod q is less than 1, both this series as well as this product, it converges. How do we? Yeah.
Sorry, Professor Atul, would you like to take question? Now
Sure.
There seems to be a question. Mithali, you have a question?
Yes, sir.
Sure.
Sir, can you please show, like I'm not getting the formula exactly. So if you can show an example with a smaller number that you put, like you put the value of P and Q. So can you show an example?
Okay, so you mean you are not able to see this formula, right?
No, I'm able to see that formula, but I'm not getting that formula.
Yeah, sure. I'm going to prove it now for you.
So can you please prove it with values, like instead of these variables?
So when you have a generating function, you will be having this variable, but you will see very soon, how you get this particular expression for this. And then we are going to make use of it to apply it towards getting actual results on partition values.
Okay,
So
sure.
I think you'll get this idea, you'll get a hang of it once you look at this proof. So how do we get this second equality? So we start with this infinite.
Atul sir. The other questions, would you like to take after you finish the proof, or you want to just have a quick sense of what doubts they have in mind right now?
Sure. Yeah, it will be helpful if I know what kind of questions they have.
Okay. So Nishit.
Hello.
Yes. Hi.
Hello, sir. Sir, what is the formula for this? I didn't get the formula.
So the formula is this itself.
No, I meant for the partition function.
Oh,
P of n.
well, that will take some time to get into. That's a very complicated formula. Actually, it's very surprising that something which is such a simple concept has a very complicated formula. So that perhaps we won't have a time to prove at all, because proving that formula is a 1 semester course in PhD coursework. So I have been through it in summer of 2007, but we will get to the generating function formula, which is very easy to do, and it requires no more than geometric series formula.
So what will be the shall I say?
So if you want to know the type of formula, I think I will suggest you wait till 25 minutes more for that.
Yes. So
Okay.
Arjun, Parth, Arav, Devang, and Anju, if your question is similar to Nishit and somebody else asked, you can lower your hand. If it is something else, then you can keep your hand raised. Parth, you have something else to ask?
Yes, sir. Sir, in this formula, is Q a constant or is it some variable?
It's a variable.
Complex number.
Yeah, it's a variable. Yeah,
Okay.
It's a complex number. So you are now regarding this as a function of q, and this also as a function of q. This left hand side is independent of n, right? Because n is the index of summation. So this is an independent of n, and so is this. Both are just functions of q.
Okay, sir.
Arav,
Oh yes, sir. So actually, like I had some like clarifications regarding the summation formula. It's just we are trying to represent in a compact form so that we just don't have to write p of 1 plus p of 2 plus p of 3 up to infinity. So that is why we are representing this formula in the form of summation so that it is easy to represent and it is easy to recollect, right?
You are right, but as far as getting another representation, this one is concerned, it has a lot of applications. That's why we write it in this other way. Any concept that you have, any object that you have, it's always good to have as many representations as possible so that you can do different sort of mathematical methods and try to understand that object, right? So yeah, this writing this one, sorry, I don't know why it is moving. Writing this one in this form is a compact way. You're right. This is a compact way of writing that generating function. Okay. So should I move forward?
Arjun, you have a question?
Okay.
Let me just check.
Sir,
Yeah, go
hi,
ahead,
sir.
Arjun.
Why wouldn't a recursive formula be easier for this? Like a formula based on previous values of p of n, and why define an explicit formula?
That's a good question. So I will be talking about the recursive formula. That's what Macmillan actually used to calculate up to p of 200. But you see
Yes,
that
sir.
it is computationally very expensive because you need to know all of the previous values. So even for a person who was very fast calculator, it took a month to go only up to p of 200. Imagine how much time it would require for anyone, even a computer, to do it recursively. Let's say p of 1 million. It will take quite a bit of time. Whereas here, it's not like you need to know all of the previous values in order to get to the current value, p of current value. You can just put n, there you put the formula, there you get the answer. That's it. So that's how it is now done in the
Yes.
computer software nowadays. So I'll come
But isn't that
to
more
the
feasible
recursive formula though.
from the human point of perspective?
So recursive formula up to small values, it is useful and it does have some applications as well. But when you have n very large, even for, I mean, for humans, that other theoretical formula that Ramanujan and Hardy have obtained, that's actually the better one. But I'll go over the one, the recursive one that you were saying. Yeah.
So in the interest of time, I think we can go ahead.
Sure.
Uh,
Okay. So we have this particular identity to be proved or this particular result to be proved. And we start with the right hand side. We have this infinite product. You all know that if I have mod q less than 1, then mod q square is also less than 1. Mod q cube is also less than 1. And in general, mod q to the any power is also less than 1. So I can expand every one of these objects, 1 upon 1 minus q, 1 upon 1 minus q square, 1 upon 1 minus q cube, as an infinite series in itself. So summation n1 going from 0 to infinity, q to the n1. You know 1 upon 1 minus x is summation x raised to n. That's what I'm doing. Similarly, 1 upon 1 minus q square will be summation, I'm using another index, n2 equal to 0 to infinity, q raised to 2n2 because it is q square to the n2, and so on. But this itself is infinitely many such sums. And so I can compactly write it in this way. I have, this is an infinite fold sum, n1, n2, n3, n4, n5, all going from 0 to infinity. And what I do is just to take the exponents of q in all these products together. So n1 plus 2n2 plus 3n3 and so on. So this is what I get. Now, what is the main idea is I would like to call this as n, and then I want to find out how many times do I get q raised to n in this particular expansion of this product. And I will tell you a hint, this number is going to be p of n, and that's how we get to the formula. But what I want to find out is if this particular sum is equal to n, I'm calling this as n, what is the first thing that should come to your mind?
So it's a sum of
So the
natural numbers
index.
which adds up to n. So it will be like a type of partition.
We are getting close to it, so that's also a good idea to think of it as a partition. Yes, that's the main idea. But one
Sir,
thing is that
Sir, we can just think of it as N1 is the number of parts of it which have 1 unit, N2 is the number of parts of it which have 2 units, and so on.
that is what is the exact idea. Very nice. But what I want to know is here, you should first think that after some point, maybe I is a very high number, N1000, let's say, N1000, N1001, N1002, and all others must be 0. Because if all these ni's are non-zero, what is this number on the left hand side? Infinity. And the one on the right hand side is finite. That cannot happen. So after a while, all of your ni's should be 0 in order to have both sides a finite number. This n may be very large, and so you may have to consider many such ni's. But as I said in English, it's all but finitely many of these ni's should be 0, except for first finitely many, which can be 10 trillion, for example. But after that, all of them should be 0. Okay. Now, as I'm repeating this question. So if we write this multi-sum as a single sum using this, so I'm just writing this as q raised to n. Then what is the coefficient of q raised to n? How many times I'm going to get, for example, q raised to 4 when I expand all this in this particular way? And now, as one of you very rightly pointed out, we need to attach a meaning to these ni's. So each ni has a meaning, that is, ni denotes the number of times I is appearing in a particular partition of A, n. So for example, n1 will tell me how many times 1 appears in a partition of n. n2 will tell me how many times 2 appears in a partition of n. Similarly for n3, n4, n5, and so on. And that actually is telling us how many partitions of n there are. Those many times I'm going to get q raised to n. And let me explain that by means of an example to you. So I'll do it on my iPad. So Vinayji, I'll just join again through my iPad, if that's okay.
Yeah, you can join through your iPad as an additional device.
Yeah.
Okay.
And I think I can share my screen. No, can you enable sharing of the screen? It's called Atul's iPad.
Rohi, can you do that? I'm not the co-host.
You should be able to do it now.
Okay. Unfortunately, it still says you don't have permission to share.
You have to stop sharing on one device.
Oh, so I'll have to stop sharing from here. Okay. And then maybe I'll have to do it. Sure. I'll do this. This will take only 1 minute. So can you all see my screen? My iPad screen?
Yes, sir.
Yes, sir.
Okay, great.
Yes, sir.
So what I'm going to do here is I'm going to look at this 1 times n1 plus 2 times n2 plus 3 times n3 plus ... is equal to n. Let's say my n is equal to 4. And so first thing that should come to your mind is that every one of these n5, n6, n7 all must be 0. Because see, here it will be 4 and 4 and then 5 and 5. If n5 is equal to even 1, then this is a number which will be greater than this 4. So all of these should drop. We won't have any of these n5, n6, and 7 as non-zero numbers. Only up to n4. So let me write down that n4. So we have actually this particular system of linear equations to solve. And now if you have this, n is equal to 4, what are the various possible values these n1, n2, n3, n4 can take? Maybe I can have n1 is equal to 4 and all of this n2 equal to n3 equal to n4 equal to 0. But then according to our meaning, This is denoting how many times 1 appears in the partition of 4. If n1 is 4, I'm saying 1 appears 4 times. That means this partition 1 plus 1 plus 1 plus 1. If n1 is equal to 2 and n2 is equal to 1 and n3 and n4 both are equal to 0, then what do you get? 2 times 1 and then 1 times 2, which is 2 plus 1 plus 1. Okay, similarly, you may have n4 is equal to 1 and all others, n1, n2, n3, they are equal to 0, which means that you are only considering the partition of 4 as 4 itself. Or you can have n3 is equal to 1, n1 is equal to 1, n2 and n4 is equal to 0. So you will have 3 plus 1 as the partition, and let me write down the last one. n2 can be equal to 2 and all others can be 0. n3, n4 is equal to 0. So I will get 2 plus 2 because there are 2 n2s. So 2 times 2. So how many of these do I have? It's exactly how many partitions of 4 I have, right? That's why q to the 4 will appear in that infinite product p of 4 times. And there is my formula. Do you all see this? So that's how, if it is true for n equal to 4, and similarly with the same meaning, it will be giving me p of 5 q to the 5. So q to the 5, if I look at its coefficient in that infinite product, it must be none other than p of 5. So this is the key concept. Let me stop sharing from here and come back to my laptop. Yeah. So let us try to see now how to use this particular formula. What is so special about it? So let me give you one interesting example. I'm looking at 11 partitions of 6. Okay, how many partitions of 6 there are? 11. Why? Here are all of them. Okay, now you are going to put some restrictions, as in you are going to ask how many partitions of 6 I have in which all of the parts are odd. So I cannot consider 6 itself, right? Because 6 is an even number, but I can consider 5 and 1 because both 5 and 1s are odd numbers. I cannot consider this one, but I can consider 3 plus 3 and so on. So if you look, there are 4 such partitions of 6 into only odd parts. Now I use another restriction. How many partitions of 6 I have into distinct parts? Distinct means I don't want such repetition, 3 plus 3. I only want something like, let's say 5 plus 1. Okay, or 3 plus 2 plus 1, because they are not repeating. So how many of them? These are also 4 in number. 6, 5 plus 1, 4 plus 2 and 3 plus 2 plus 1. None other than these 4 can come into this set because they have repetitions. Like here, 1 is repeating 6 times. But now this number is same as this number. Is it a coincidence? Is it only a property of number 4 or is it a property of general number n?
Sir, it is for general number n. I know this one.
Yes, so that's what we are going to prove using generating functions. So this is a theorem of Euler, very beautiful theorem. The number of partitions of n into odd parts always equal the number of partitions of n into distinct parts. Okay, so one way to show this is to look at the 2 sets. Let's say set A consists of number of partitions of n into odd parts. Set B consists of number of partitions of n into distinct parts, and you show that the cardinalities of the sets A and B are the same.
Sir, we can also say that generating function of both of them is equal.
That is what I'm going to do. But I'm saying if you want to prove it without using generating functions, what you do is you actually you start with a partition into odd parts, and then you create a bijection, and you show that, okay, this can be mapped to a partition into distinct parts. And so that if you reverse that map, you are going to get back to the same partition that you started with. If that is the case, because the two sets are finite, their cardinalities must be same. If you have a bijection, and that will say, okay, you have a result. But we are going to now prove using generating functions. So here is how the proof works. I'm going to call by A of n the number of partitions of n into odd parts, and by B of n number of partitions of n into distinct parts. And then I want to show A of n is equal to B of n for every natural number n. This is equivalent to showing their generating functions are same. Can anybody tell me why? Why is this, if I
May
show
I?
two generating functions are
Sir,
the
I
same, why
think
does that
we
imply
can.
an equal to b of n?
Sir, I think we can write it as summation j running from 1 to infinity. The generating function of a of x as summation j running from 1 to infinity 1 plus x power j, and b of x generating function as summation k running from 1 to infinity 1 over 1 minus x power 2k plus 1. And then after doing some rearrangement
No.
and
I'm not saying
algebraic.
about actually partitions into distinct parts or odd parts. I'm just saying in general. Forget about these two denoting these partitions also. How
So that
does
is
it
because of
follow?
polynomial. I mean, both of them are polynomial, and for each q, if they
Not
are equal.
polynomial actually, but because they are linearly independent.
Oh yes,
You
sir.
know the
Sorry.
the monomials 1x, x square, x cube, dot dot dot. That whole set is linearly independent, right? Because it is linearly independent. If I take this on the left hand side, let's say, then I'll have summation a of n minus b of n q to the n is equal to 0. And there is no relation between them whatsoever. So an minus b of n will be equal to 0. I mean, because a minus b of n, a of n minus b of n times q to the n is equal to 0, but q to the n is not always 0. So a of n minus b of n should be equal to 0. And that means you have this. So it comes from linear independence. And so now if I have same expression for these two generating functions where a of n is denoting the number of partitions of n into odd parts and the one into distinct parts, then I'm done. So I go with this, and you see I will have this as the representation, as one student rightly pointed out now, because what I'm doing is I'm taking that Euler's representation 1 minus q square, 1 minus q cube, 1 minus q raised to 4, 1 minus q raised to 5, and I'm removing all those which are generating the even numbers. 1 minus q square is removed from in between here. 1 minus q raised to 4 is removed from in between here. I only want those numbers which are odd parts. So this is the generating function. Now, for distinct parts, I claim that this is what you get as the generating function. And the reason is, say, what is this? This is the truncated part of the geometric series 1 plus q square plus q cube plus dot dot. This is the truncated part of the geometric series 1 plus q square plus q raised to 4 plus q raised to 6 plus dot dot dot. And similarly for all of these. So why are we doing these truncations? Because suppose I have in general m as my part. Okay. So what is, how do I expand it as a geometric series? 1 plus q raised to m plus q square, q to the 2m plus dot dot dot. And 1 I'm writing it in this form, 0 times m in the exponent. So now m is my part. I want, what are these numbers denoting? How many times m comes as a part? So if I'm looking at distinct parts, then either that part does not appear at all, but if it appears, it cannot repeat. So it appears only once. So it occurs at most once. And that's why you cannot have these, only except these first two expressions, you cannot have all of them, because this is saying that m appears twice or thrice or 4 times and so on, which you cannot have. So that's why in general it is 1 plus q raised to m. So when I am having m as 1, I'll have 1 plus q. When m is 2, I'll have 1 plus q square. When m is 3, I'll have 1 plus q cube. So I have now analytic expressions for both these generating functions into odd and distinct parts respectively. These are here, right hand sides of 2 and 3. And so if I show these two are equal, then these two are equal, and that means n equal to b of n.
Atul sir, we
Yes.
have questions. Is it okay if we take the
Sure.
questions now?
Sure.
Mitali, can you unmute yourself and ask your
Sorry,
question?
sir, I forgot to lower my hand. I wanted to answer them. That's
Oh, sorry. Okay. Yes, Parth.
So I didn't understand the last part.
Okay. Yeah. So here the question is that how many times m should come if I'm taking partition into distinct parts? Either it comes 0 number of times or it comes once, right? Because if it comes more than once, then means it is repeating. So it's no longer a distinct part.
Yes.
So what is m repeating is telling me here. It's coming from here. Either m is appearing 2 times or 3 times or 4 times or 5 times and so on. So this thing should not be there. Sorry. This thing should not be there. So it will be only 1 plus q to the m. Okay. And you now put m as 1, 2, 3, 4, so on. So that is 1 plus q, 1 plus q square, 1 plus q cube. So on.
Okay, sir, got it.
Sure. So now I want to show the right hand sides are equal. And again, if you want to show that rigorously, because you are looking at infinite products, there are questions of convergence and you have to go to various tests of convergence. But let me now do it sort of formally, because our intent here is to get an introduction to this area. So I have these two infinite products which I want to show are equal.
So a couple of more questions are there.
Okay, sure.
Raghav, can you unmute yourself and ask the question? Raghav, are you there? We can't hear you.
Hari, we may want to go ahead with his permission because there are 20 minutes left and they have another session after this.
Okay.
Okay.
Sure.
Okay.
Yeah. So if you see, how do we prove? We start with the left hand side and we fill the missing expressions. So I did not have 1 minus q square in between these two. I did not have 1 minus q raised to 4 in between these two. So I multiply top and bottom by that. And so you get this. And now I just use a square minus b square as a minus b times a plus b. So 1 minus q square upon 1 minus q will be 1 plus q. 1 minus q raised to 4 upon 1 minus q square will be 1 plus q square. And 1 minus q raised to 6 upon 1 minus q cube will be 1 plus q cube, so on. So this is exactly what we wanted to show. And that is proving Euler's theorem for every n. I don't have to go by means of an example. I have a rigorous proof for every n, natural number n. Okay. So where are partitions applied? Is it just something that we do for fun? No, it is, apart from intrinsic beauty and apart from having it study on its own to be done, they are also having applications in many areas of science and engineering. For example, they are used in non-parametric statistics, statistical mechanics, probability and statistics, particle physics, computer science, group theory, basic hypergeometric series, modular forms, mock modular forms. These are last three were very much connected with partitions. So who were the people who really started this area? So earliest person seems to be Euler, then Gauss, then Jacobi, Sylvester. Sylvester had a big school in Johns Hopkins University in the US after he moved from England, and there he established very crucial results in partition. Then comes Hardy, Ramanujan. Then comes, there are many people in between. I have only included a few of them. So George Andrews is considered to be the world's leading expert in the area of partitions. And Freeman Dyson, who unfortunately passed away last year. So let me give this story that I described about the exact formula. So Hardy and Ramanujan asked McMahon to calculate P of n up to n equal to 200. So here is the recursive formula that somebody was asking there. P of n is expressed in terms of these numbers, but there are not all of them, okay? There are numbers of a particular kind, of which if I have time, I will come back to. But you have a recursive formula, which McMahon also used to calculate P of n up to 200, and it took him a month. And later, our own Indian mathematician, Hansraj Gupta, extended that table up to P of 300. See, this is before the advent of computers in 1930s or so. Nowadays, you have Mathematica software. You put P of 10,000, it will give you an answer within maybe a fraction of a second. But if you want to copy that answer, probably it will take you perhaps at least half an hour. Anyway, so how McMahon did was he arranged the values of P of n in groups of 5, where we start with 0. P of 0 is assumed to be by convention equal to 1. Okay, that's actually convenient. Don't think much about it. It is just because it is convenient to do that. So he started from P of 0 up to P of 4. Then he put a dash. Then he started with P of 5 up to P of 9. Then he put a dash, and so on. And then he gave the list to Hardy. Hardy passed on the list to Ramanujan. So here is how it is looking. This is from Hardy and Ramanujan's paper, but Of course, the values are same as McMahon gave. So they have omitted P of 0. Okay. So as I have said, after 4, they put a line. After 9, they put a line, and so on. I mean, McMahon put a line. So can you spot something special for P of 4, which is 5, P of 9, 30, P of 14, 135, P of 19, 490, P of 24, 1575. Is there anything special?
Sir, multiples of 5.
Exactly.
5.
Exactly. So before P of 5, there was a line drawn. So perhaps people may think, oh, what's so special about Ramanujan discovering that P of 5n plus 4 is congruent to 0 mod 5. It is, one could have also done it. But see, McMahon himself prepared the list. He himself put that line, but he did not spot it. He sent it to Hardy, another great mathematician. He also did not spot it. And Ramanujan spotted it instantly. But he went beyond. So what he did was he also looked at, now there wasn't a line after 7, but he looked at P of 7, 15, sorry, P of 5, 7, then P of 12, 77, P of 19, 490. Can you spot something?
Sir, multiples of 7.
Multiples of 7.
Multiples of 7. And here, very nice. And similarly, if you look at 6, 17, you see this is 11.
Sir, multiples of 11.
These are multiples of 11. So Ramanujan actually gave these 3 congruences that they hold, and that actually revolutionized this area. Why? Because partitions were thought of as something involving only additive process, whereas what Ramanujan is claiming here is that you have multiplicative properties. So that was stunning. And not only that, he also discovered what Hardy calls as Ramanujan's most beautiful identity. What is that identity? He actually has a generating function for P of 5n plus 4. And why is this so special? Because it has a 5 in front. So this gives this congruence trivially. Just by looking at here, you see that, okay, because I have a 5 in front, all of these P of 5n plus 4 should be congruent to 0 mod 5. He had a similar such generating function for P of 7n plus 5, by the way, where instead of having one infinite product, you have sum of 2 infinite products. And in front of that first infinite product, you have a 7. In front of the second infinite product, you have a 49. So that also tells me that I have 0 mod 7 congruence, very trivially. For 11, it is much, much more complicated. That was only obtained 1 or 2 years back. But anyway, Ramanujan did have proofs of all these identities or congruences. And let me skip through some of this because I don't have a lot of time. But what I'm going to show you is that Dyson, Freeman Dyson, about whom we saw a picture, he asked, do you have a simpler way to envision the congruence? So he asked, is there any statistic by means of which you are actually able to say, okay, how partitions of 5n plus 4 are divided into 5 equinumerous classes? And then he himself, as a 16-year-old kid, so almost of your age, so he wrote his first paper, which is still considered to be a classic. It was written in 1944. So he found that statistic. He called it as a rank of a partition. And he said that, okay, rank of a partition, I call as largest part minus the number of parts. And that will do the job. Let's see how. So here is pi as a partition. Don't think of pi as 3.14, that same famous number. Pi is just a notation for a partition. The rank of a partition pi is called as largest part of pi minus the number of parts of pi. Okay. So what I'm doing is I'm giving you an example of all partitions of 5. We know there are 7 in number, and I classify them according to their ranks. So what is the rank of 5? Largest part 5 minus the number of parts 1. So that is 4. Largest part 4 minus number of parts 2. So that is 2. Then let's say, let me not do all of them, but last one is largest part 1, number of parts 5. So 1 minus 5 equal to minus 4. So you look at all these ranks and you classify, look at them modulo 7. So 4 will remain 4, 2 will remain 2, 1, 1, 0, 0, but minus 1 will be 6 mod 7. Minus 2 will be 5, minus 4 will be 3. And you see that each of the residue class appears exactly once. And that is not only true for 5. In fact, Dyson made this conjecture that if you look at any number of the form 7n plus 5, then the number of, this is what I'm going to explain now. The number of partitions of 7n plus 5 with rank congruent to 0 mod 7 is same as the number of partitions of 7n plus 5 into rank congruent to 1 mod 7 and so on up to 6 here. So that tells me that, okay, rank has distribution of partitions of 7n plus 5 into 7 equinumerous classes. Once you have 7 equinumerous classes, you get the congruence. But he did not prove this. He had this as a conjecture. He had a similar conjecture for 5n plus 4. And then this conjecture was actually proved by Atkin and Shinnerton Dyer 10 years later in 1954. Okay. But he observed that rank does not distribute partitions of 11 plus 6 into 11 equinumerous classes. What happens is that if you do the same thing with partitions of, let's say, 6, you have 11 of them, you classify them according to the rank and look at them modulo 11, you will not have every residue class represented only once. You have some of them which do not appear, you have some of them which appear more than once. And so because of that, it doesn't distribute that into equinumerous classes. So how do we see one congruence? P of 11 and plus 6 congruent to 0 mod 11. So he's conjectured that there should be some partition statistic different from rank called crank, which would do this. And that crank was found after 44 years. So it was found by George Andrews and his PhD student Frank Garvan. So actually Frank Garvan had found it initially, but for some special classes of partitions called as vector partitions. And then they together, they found this. So there is a very, very nice story about this. So in 1987, there was a conference at my university, University of Illinois at Urbana-Champaign, celebrating Ramanujan's centenary. Because you see, Ramanujan was born in 1887. So 100 years later, they had this world famous conference where world famous mathematicians from all over the world working in this area came. And there, the conference happened, and these two had a flight to their respective destinations next day in the morning. So they were staying in the same building in adjacent rooms. And after the conference ended in the evening, they did not have anything to do as such. Dinner was done and all. So they both decided that, okay, let us work on that aspect of finding crank. And that same night, they were able to do this. So Professor Krishnaswamy Alladi very rightly said that probably it was the intention of goddess Namagiri, whom Ramanujan really revered so much, that the crank should be found during the Ramanujan Centenary Conference itself. So it's a very nice thing. So anyway, this was a very big achievement. It actually opened doors to many other things in partition theory, which are still studied. I won't be able to go into crank definition because it is slightly involved. But let me come back to this formula, which I showed you on the second slide. So this is the asymptotic for partitions. How does the exact formula look? The exact formula was really an improvement of Ramanujan and Hardy's formula done by Rademacher, and he got this formula. So somebody was asking me about what this formula looks like as an exact formula. Here it is. So P of n is given, and it's very, very surprising. Why? Because you see Bessel functions coming here. What are Bessel functions? They are some solutions to second order linear differential equations, homogeneous linear differential equations. What does that have to do with counting of partitions? What is this an, ak of n? This is called as Klustermann sum. That is also something very, esoteric. You have here what is called as a Jacobi symbol. I don't have even time to go into all of the definitions of these things, but all of these are actually coming into the definition of partitions, the formula for partition. So don't think of it as, okay, I'll not be interested in this particular quantity because this was such a simple concept to calculate. And this is so complicated. But this is very useful because you have very fast methods, fast algorithms to calculate all these values. Okay. Actually, this order of this Bessel function is 3/2, which reduces it to an elementary function involving hyperbolic functions. But I have put it as a Bessel function itself. So with the help of this is what is implemented in today's computer software. You actually get many results from here itself. So let me actually go with certain other things in the remaining. So Vinayji, I have 5 minutes, right?
Yes, yes, yes.
Okay. Yeah. So what I would like to say is about, maybe let me see whether I'll be able to even talk. So you have seen reciprocal of this, which is a generating function for P of n. But what about this itself? So Euler actually wrote that as a sum. So it's like, okay, if I expand this as a sum, if I multiply out everything and write it as a sum, how does it look? Can I make any inference out of it? So it is this. So this is called as Euler's pentagonal number theorem, because on the top you see only pentagonal numbers. If you put n equal to 1, 2, 3, 4, 5 there, you'll see that those, if you represent all those numbers by means of dots, you can actually draw pentagons with the help of that. So these are called as pentagonal numbers. Okay, so this is a result of Euler, which was combinatorially interpreted by Legendre. And how did Legendre do? He said that, okay, instead of minus signs, if you have a plus sign, that means you have partition into distinct parts. We have seen that. Okay, it's a generating function for number of partitions into distinct parts. So I take partitions of n into distinct parts and I classify them into two groups. I actually take dE of n to mean number of partitions of n into even number of distinct parts. See, the parts themselves can be odd, but number of such parts should be even. And similarly, I have dO of n to denote the number of partitions of n into distinct parts which are odd in number. And then this theorem is equivalent to saying that these two are almost always equal, meaning they are zero almost always, and they are non-zero and differing by only plus or minus 1 if n is one of these pentagonal numbers. And there is a purely combinatorial proof of this, which Franklin, who was a student of Sylvester, found. But let me omit that proof. Let me give an example though. Here are 7 partitions of 5. Okay. And these 7 partitions of 5, I want to now break into first distinct parts. So how many distinct partitions of 5 I have which are even in number? There are only 2, 4 plus 1 and 3 plus 2. See, they can contain odd parts, but the number of such partitions into distinct parts, I mean, number of such parts should be even. 2 parts, 2 parts. So dE of 5 has these 2 partitions considered. What about dO of 5? I want partitions of 5 into distinct parts, and I also want them to have odd number. So there is only one possibility here. Which one?
5.
5.
5 itself. Yes, yes, 5 itself. So there is only one part. So dO of 5 is 1. And then I see that dE of 5 is not same as dO of 5. They are differing by 1 because 5 is not a generalized, because 5 is a generalized pentagonal number. How? You see, if I put r equal to 2, 2 times 3 times 2 minus 1 upon 2 is 5. I take minus sign here. So when r equal to 2, you get 5. So then our theorem matches. But if you had taken that for 6, then I would see that both dE of 6 and dO of 6 are the same. Okay, now let me, in the remaining 2 minutes, let me skip this proof of Euler's pentagonal number theorem. But let me go very briefly into what are one of the most famous identities attributed to Ramanujan. This is called as Rogers-Ramanujan identities. So these are sum product identities, where on the left hand side you have an infinite sum, on the right hand side you have a product. Okay, there are no simple proofs of Rogers-Ramanujan identities even up to now. There is one proof of David Brasou, which is called as the simplest proof up to now, but still it's quite complicated. Nobody has been able to find a simpler proof up to now, even after 125 years, if I believe, of finding these. These were first found by Rogers in 1894 and then rediscovered by Ramanujan in 1914. Here is Rogers. And let me actually skip this part, but let me say that connected with Rogers-Ramanujan functions, which were the sums that you had on the left, is what is called as Rogers-Ramanujan continued fraction. So all of you must have studied this continued fraction. Continued fraction is something which has infinitely many, I mean, it just keeps on going. It's 1 upon 1 plus 1 upon 1 plus 1 upon 1 plus 1 upon 1 plus dot, 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 dot. So how do you show that it is equal to this 1 plus root 5 by 2? Anybody? Do you have an idea? So here is a non-rigorous way to see it. You take this as x, then what will be 1 upon x? 1 upon x will be this 1 plus, again the same thing. So 1 upon x is 1 plus x. You solve for the quadratic. You know that this is a positive number. You discard of the negative one. You will get, I mean, the negative quantity. Then you will get the positive root as 1 plus root 5 by 2. Right? This is something that does require, first of all, an analysis into the fact that this thing actually converges, and that's actually not very easy. But anyway, if you assume that convergence, then this can be rigorous. This can be easily done. So what Ramanujan did is that, and also Rogers, he, instead of these ones, here 1, he put q square, q cube, dot, dot, dot. And then here he put q raised to 1 by 5. Why 1 by 5? Why so complicated thing? It is because it makes things simpler. But anyway, they found here, so when q is equal to 1, you get this back. But they found that this continued fraction is given as an infinite product. Okay. So let me now say that infinite product can actually be evaluated at certain quantities, about which Ramanujan was an expert. And Hardy commented, these were given in his first letter to Hardy. And Ramanujan said, these formulas defeated me completely. Hardy said this: I had never seen anything in the least like them before. A single look at them is enough to show that they could be written only by a mathematician of the highest class. They must be true, for if they were not true, no one would have had the imagination to invent them. And these Rogers-Ramanujan identities, sorry, I didn't have much time to say this, but they are used in number of areas of mathematics and other parts of sciences. V algebra, statistical mechanics, algebraic geometry, K-theory, conformal field theory, group theory, these different types of algebras, knot theory, orthogonal polynomials, probability, transcendental number theory. So lastly, let me skip the statistical mechanics part because it will take some time to discover. But here is the last quote that I would like to say. It's a quote by Sylvester. Sylvester says, partitions constitute the sphere in which analysis lives, moves, and has its being. And no power of language can exaggerate or paint too forcibly the importance of this still recently almost neglected but vast, subtle, and universally permeating element of algebraical thought and expression. This is what he wants to say about partitions. Universally permeating element of algebraical thought and expression. Why? Because counting is what is at the foundation of all of mathematics, right? And so partitions are very, very common in many areas. So with that, I would like to stop. Thank you. Sorry for going over time.
Thank you so much, Professor Atul, for that wonderful presentation. I got a lot of questions on chat, and because of time constraint, we couldn't take that. But there are 3 hands raised. If you guys have quick questions, we can take them. Raghav, Imran, and Sarah. Okay, so Raghav, you have a question?
Yes, sir. I didn't understand the formula, but I understood like multiples of 7, multiples of 2, 6. That is okay, but I still did not get the formula with that infinity symbol and all.
Yes. So you mean the one where we have an exact formula for partitions, right?
Yes, to find the partitions of the numbers, like the standard formula, I didn't understand.
Yeah. So this one will actually take some time to calculate here by hand, because you have these transcendental functions like Bessel functions and all coming into picture. This also requires time. But algorithmically, by computer, this is very fast. So you may say that, okay, I could actually find partitions of 4, 5, or let's say up to 10 quickly by hand than by this formula, because one needs to get used to these kind of formulas, these expressions. But very soon, if you have your n large, this formula will beat the hand calculation, because you have these algorithmically built. You can actually have this entered into computer, and then you can put it any value of n, and you get the answer in fraction of a second. So I know this to calculate by hand, you don't need to really get up to infinity. If you have n as small number, perhaps you can get some few values and then you'll get a number which is very, very close to p of n. And it might be having a fractional part, you discard off that fractional part because you have only an integer that you want. Yeah.
Sarah?
Sir,
Sorry, Sarah, we can't hear you. Devang?
Sir, what does that asymptotic sign mean?
Asymptotic sign means, suppose f of x is asymptotic to g of x, that sign. That means, as let's say extend to infinity, that means that limit extends to infinity, f of x upon g of x is 1. So crudely speaking, it says that, okay, when your x gets very large, f and g are almost the same.
Okay, thank you, sir.
Satya?
Sir, yes, sir. Can you go on to the next slides?
Which
Next one, the slide which has the fractional part.
In the continued fraction?
Yeah.
Oh, okay. Yeah.
Yeah. Here, 1 by 1, isn't it 1? How is it equal to 1 plus root 5 by 2?
No. This, sorry. This notation, this plus sign is not in between. Okay, this is actually denoting 1 upon 1 plus 1 upon 1 plus 1 upon 1 plus 1 upon 1 plus 1 upon up to infinity.
Oh, okay. Now it makes sense.
So Bruce Berndt wrote this volume of Ramanujan's last notebook, Ramanujan's notebooks, part 3, where he said that he had written the continued fraction in this notation, which is what is followed universally. And the copy editor from Springer, he thought that this was a mistake and he put all these plus signs in between. And then he again had to correct all of this for all of these chapters that he had. So
big blunder.
Yeah.
They had to reprint or something, or
no, it didn't get to printing, but
luckily.
it was the proof checking. When he did the proof checking, he found that, oh, he has made this in between, and then the answer changes. I mean, it will be infinity, right? It won't be a finite number.
So you also said that notebooks part 3. I assume you don't like to call it as the lost notebooks as
no. So because from Ramanujan had 3 notebooks, and then the lost notebook was found only 56 years after he died.
Right.
So on those 3 notebooks of Ramanujan, Bruce Berndt wrote 5 volumes called Ramanujan's notebooks, and then on this one lost notebook, Bruce Berndt and Andrews wrote again 5 volumes. So, and just note that Ramanujan wrote lost notebook when he was in the last year of his life and when he was almost ill all of that last year. But that on that last year's work, people have written 5 volumes and people are still studying. So somebody, Richard Askey, who is himself, he was a very great mathematician, he said that Ramanujan's lost notebook is a lifetime work of a very great mathematician, and that was done in 1 year when he was very ill.
So this continued fraction says 1 by 1 plus 1 by 1, so it's ultimately 1, no sir?
So Raghav, what we can do is, in the interest of time, we can just write it and share it in the Google Classroom, and then you'll get a better sense of it. So there are a few more hands raised, but I'm afraid we are running short of time. We have another session to start at 11:30. And before that, I just wanted to, make a quick comment. Can I stop sharing the screen?
Sure.
Sir?
Yes.
Okay. Just wanted to make a quick comment and then, go ahead with the vote of thanks. So we have Sohalia. Are you there? Can you just...
Yes, sir.
Yeah, can you just switch on your video?
Yes, sir.
Okay. So we have Sohalia. Sohalia's parents were co-producers of the movie The Man Who Knew Infinity.
Oh, wow.
Yeah.
So your last name is Bhise?
Sorry, sir?
Sohalia Bhise?
No, sir. No, sir.
Oh, okay.
Okay. So, so we have lot of
Wow.
connections in this
Yeah.
session itself. So yeah,
Nice.
and yeah, so that's about it, Atul sir. I just wanted to thank you very much for this wonderful session, and
Thank you.
maybe some remarks by or some feedback and vote of thanks by Malay Mahajan. And the reason I'm calling Malay is because Atul Dixit sir was student of our Sri Prasad Tambe sir, who's taking sessions, and Malay is also a student of Tambe sir.
Oh.
So I thought, let two students thank each other. So, Malay, over to you.
Good morning, everyone. On the behalf of all students of RAMTP 2021, I, Malay Mahajan, take this opportunity to thank Mr. Atul Dixit sir for spending your precious time to give knowledge on this amazing topic and for the fascinating stories of the great mathematician Ramanujan. I hope we will surely get a chance to hear more from you in the future. Thank you, sir, once again.
Thank you very much, Malay.
Thank
Let
you.
me write in chat the two books that interested students can actually take a look at.
Please.
So the first one, which is kind of elementary, it's actually a good idea to start with that book. That is called as Integer Partitions, and that is written by George Andrews and Kimo Erickson. And once you are done with that, then or you can parallelly also start, but this one is slightly advanced. Theory of Partitions by George Andrews. Oh, okay.
No.
Yeah.
I'd put it as host only, so that
okay.
you're not disturbed by the message.
Right.
Yeah. So I'm getting all the thank you messages from everybody. I just don't want to open the chat so that they can note down these names.
Sure.
But I'm receiving a lot of thank you messages for you.
Thanks. And as you said over the email, I will share the slides with you, this one, so that you can share.
Wonderful. That was also another question which some of them had.
Okay.
Right. Thank you so much, sir. We really know how much how passionate you are, and we could really feel that in the session. And I really hope that all of us get more such opportunities to interact with you, to learn from you. And I hope that some of them be your PhD student in future. Who knows?
Yeah.
Okay.
Thank you so much, Vinay.
Thank you so much, Atul sir. If you have 2 minutes to stay back, can you stay back, Atul sir?
Sure. Yeah.
Okay. So, students, I